Great. Okay. Thank you very much for inviting me. And yes, I would like to start with a little showcase of the theoretical toolbox that we use in first principle calculations. Most people here by now should be familiar with DFT, which we know is a method for describing ground state properties such as total energy and forces and predicting the structures. But when we talk about first principles in ab initio, we can go much further into the kind of interactions we want to describe. First of all, well, there's the perturbative extension of DFT called DFPT, allows you to describe phonons and vibrations of the system. So if you want to describe a chemical reaction, for example, you need, for instance, to know the 0-point energy, which is an important contribution. So you need that. But then we can go further up into the different kind of interaction. For example, the interaction between phonons and the electronic densities or the electronic states themselves. This is when we talk about electron-phonon coupling, which underlie numerous phenomena such as the electric mobility, superconductivity, or just the temperature dependence of the whole electronic structure. And finally, if we want to discuss excited states or such as optically enabled state, then we need to make use of formalism such as the Bethe-Salpeter equation that will give you access to, say, optical absorption and describe those bound states between electron and hole that you create when you absorb a photon. So today I would like to present three different projects I'm currently working on. And as we go through this project, we'll be moving up through this ladder of theory. Some of these projects, as I say, are unfinished, but I'm still very excited to talk about them. So we'll start by saying a few words about hydrogen absorption in metal hydrides. So as a mean to store hydrogen in a solid form. So we're interested in these ternary A2B7 alloys, such as neodymium, magnesium, nickel, and some rare earth doping that make this system where you have a reversible absorption and desorption of hydrogen. These systems are known to have a large hydrogen absorption capacity and to operate at moderate temperature, meaning that we don't have to raise the temperature too much if we want to release the hydrogen gas. And to describe this theoretically, we need to be able to predict the enthalpy induced by the absorption of hydrogen in the material, and also the change in entropy, because this is what will allow us to predict the desorption temperature. And from experiment, they can draw these Van Hoff plots, so hydrogen pressure around the materials versus temperature, inverse temperature, and with the slope, they can determine what is the enthalpy and what is the entropy of the hydrogen absorption process. This whole field was pretty much new to me, and the first approach we did was sort of a naive approach. We thought, okay, we want to simulate hydrogen absorption. Let's just take our material, put hydrogen randomly in the unit cell, and let it relax, and do this again and again until we have a meaningful sampling of all the possible configurations that we could do. And in the end, we can draw these histogram of the number of configuration for a given final energy for the absorption of. So this is a absorption enthalpy. So we did that, and yeah, in the end, we obtained some mean hydrogen absorption enthalpy, and it's not too far from the experimentally measured one. You know, we thought, okay, maybe if we increase the sample size, it will converge to the right value eventually. But the entropy that we get by doing this is completely horrible, completely wrong. We didn't quite know why. We thought, you know, there's many things. Maybe there are, okay, so for the entropy, we compute the phonon spectrum and see how the vibration energy change, and also the configurational entropy. But we are neglecting a lot of things. There are anharmonic effects to account for, and the sampling of the configuration needs to be very good to be able to compute this entropy. So it took us almost 2 years to get there. We did hundreds of calculations, and you know, each of these configuration requires a full DFT relaxation. So in the end, it's extremely expensive, and the sampling is quite poor. So okay, didn't work so well. So we moved on to a new approach, and this is a project we started with our collaborators at the CEA in France, where we do this machine learning assisted canonical sampling. And the idea is that we combine both DFT calculations and classical molecular dynamics with interatomic potential. And so by now it's well established that you can use machine learning to train those interatomic potential on a given set of calculation that you've done. What's new with this method is that we do this learning on the fly as we progress through the molecular dynamics. So we do a DFT configuration, then we let the system evolve through some maybe 100 steps in classical molecular dynamics. Then we do another DFT calculation and update the potential each time. Right. So we use an interface that uses both the Abinet software and the LAMPS software to do this. All right. And this is some preliminary results I'm showing here, where we see the error in the total energy and in the total force as we progress through the simulation. So it's going down very slowly, but ultimately we don't care if so we can improve the accuracy systematically by increasing the number of parameters that we allow in the interatomic potential, but ultimately we don't care too much if it's not very, very accurate, because it's just a sampling of the configuration. And in the end, it's only the DFT calculation that we use to make our average. So this is this new the distribution of configuration and their energy as we do this molecular dynamics, and we get a much smoother distribution from before at a fraction of the cost. And so we see the energy converging quite nicely as we progress. So this is project. Let's say that the second phase of the project is barely started. I don't have any more results to show, but we're very excited about this technique here. Right. Next up, I wanted to talk about MX scenes and the electrical conductivity that we can compute through specifically the phonon limited electrical conductivity in these materials. So MX scenes is this class of two-dimensional metallic system. So this is the general formula, where MXT, where M is a transition metal, X is either carbon or nitrogen, and T is a surface termination. So this is a very, so it's a diverse class of 2D materials. There's nearly 100 compounds that have been identified. Initially, they showed very good performance for doing electrode materials for lithium-ion batteries and supercapacitor. But very recently, it's been shown that they can be used for various catalytic processes, such as hydrogen production, also hydrogen storage, because these are laminated materials that we can intercalate a lot of different ions in between, so including hydrogen molecules. But we can also do hydrogen production by electrocatalysis and also nitrogen reduction. So lots and lots of applications for these materials. All right. What we wanted to look at first was how does the surface termination affects the electrical conductivity. So in the synthesizing these materials, you need to include some surface termination, and you have a choice in doing that. So we wanted to see how this affects the conductivity, and also look at different thickness of the materials with the same surface termination. So these are the 4 materials we are looking at. And here I'm showing the electronic band structure as well as the projected density of states. And so what we notice is that these materials, as soon as we put some a surface termination, these surface atoms add more states below the Fermi level, and so in some sense the Fermi level goes down and starts to intercept this highly dispersive band that is mostly the titanium D levels that now crosses the Fermi level and will be responsible for the high electrical conductivity of these materials. Right. And then we can also look at the phonon band structures of the materials and project that onto the different atoms. So the low energy phonon modes are mostly composed of the metallic atoms, while the motion of the carbon lies up here, and the motion of the surface atoms somewhere in between. So next, if we want to compute the electrical conductivity, so here I apologize for getting a bit technical here. I'm showing the Boltzmann transport equation that tells us how a given electronic states will affect the overall electric field in the material, and the response of the materials to the change in occupation of one electronic state, say at n and k, is coupled to all the other electronic states. So there's the first term here mostly describe the depopulation or repopulation of a state due to random scattering due to phonons, and it's described by this tau, this electronic lifetime. And if we do this, what we call the relaxation time approximation, the RTA, it means that we are dropping this term, coupling one state to all the other, and simply express the response of the system in terms of this relaxation time of each individual electronic states due to the interaction with all the phonons. And so we end up having this nice expression for the electrical conductivity given by the velocity of each electronic states, their lifetime, and the derivative of the Fermi-Dirac occupation factor. Now, okay, if we want to compute that, we need to sample, well, all the electronic states of the Brillouin zone, but we also need to sample the phonon states. So here I'm just showing a convergence graph, but this is what makes the calculation very challenging, is that we need to use very fine Q-point grid to sample, K-point grid to sample the electronic states, so we converge up this way. And then we need to sample, up to very fine Q-point grid, to sample all the phonon states. And here we're converging downwards here. So this is the electrical conductivity as a function of temperature. But okay, we end up, we find the optimal grid that we need to use to converge the electrical conductivity. Now, what about the electronic lifetime that enters the expression for the conductivity? There's actually several ways to compute this lifetime. The most common one is the self-energy relaxation time approximation, and this is the full energy, so the full expression for the scattering rate, or the inverse lifetime. So this is given mostly by, an integral over the whole Brillouin zone for the phonon modes, and these G here, these are the electron-phonon coupling matrix element that we can compute after doing a DFPT calculation. Right, so this is basically just the average time that you will wait between two scattering events by a phonon. There's a better approximation if we want to capture as much as possible this iterative Boltzmann transport equation, and it's just a matter of adding this efficiency factor alpha in this expression by saying, does the scattering occur in the direction of the initial state, or does it scatter perpendicular to it and disrupts the current this way? So this approximation is called the momentum relaxation time approximation. It just takes better into account the direction that the scattering process occurs. And so here we're comparing the three different framework. So the self-energy relaxation time approximation, or momentum relaxation time approximation, compare with the full iterative Boltzmann transport equation. And this is so electrical conductivity versus temperature. What we find basically is that the CERTA tends to underestimate a lot the electrical conductivity, whereas MRTA is in much better agreement. But at the end of the day, if we really want to resolve the fine details and the differences between the materials, we really need to go to the full iterative Boltzmann transport equation to get the correct ordering of the different materials, even at 300K. All right, and finally, we can decompose the different contribution to the electrical conductivity. So here I'm showing basically the three ingredients that come in this equation here, namely the squared velocity, the derivative of the occupation, and the lifetimes. So in greens, you see the electronic lifetimes of all the different states in the different materials, and in blue, you will have the squared velocity density. And so we can understand qualitatively why some materials will end up with a higher electrical conductivity. Namely, we see that just adding the surface termination increases a lot the velocity of the states, and the OH2 termination has the longest scattering lifetime, and thus it has one of the best electrical conductivity among those, while those that are thinner, the material that is thinner, also has a much shorter scattering lifetime, explaining its lower electrical conductivity. Okay, this is all. I've not put in the comparison with experiments yet. We don't quite reproduce the experimentally measured electrical conductivity. In fact, we overestimate it. At this point, I believe that it's because we are overestimating the velocity of the states, because we are not taking into account the renormalization of the velocity due to phonons. So still a work in progress. Okay, finally, I want to show you, well, something that works at least. This is my latest work on the dynamics of light-induced excitations, so namely excitons. So, right, so excitons are these bound states that you create, so bound electron-hole pairs that you create after absorbing a photon. And we can measure the lifetime of these excitations just by looking at the line shape when we do a optical absorption process. And what we notice in experiment is that at low temperature, these transitions tend to be very sharp. We tend to have very long, long-lived excitations. And these are so some experiments in perovskite nanocrystals where we really see a very, very sharp transition, and sometimes we even see in the spectral function resonance due to phonon absorption. So this is really a signature that we're talking about exciton-phonon coupling, not just electron-phonon coupling. Okay, so how do we describe this? So we like to draw diagrams in physics to explain these things, and so these are all Feynman diagrams. So these arrowed lines represent a propagator. Basically, it's the Green function. If we can compute that from the electronic states. And it tells us everything that we want to know about the system, the excitation energies, and so on. And whenever we add an interaction to the system, such as the Coulomb interaction between the electron and the hole, or the phonon interactions, then we can define a self-energy that tends to modify those propagator. So this is a diagrammatic representation of the Bethe-Salpeter equation for bound excitons. So these L represent an exciton propagator, meaning both the electron and the hole propagating and interacting with one another. Right, and on the other hand, at least we have a clear understanding of the one particle picture, so how the interaction of phonons will change each electronic state individually. So this is, we can capture this by computing the self-energy, which we represent by these diagrams here. And so this is a complex quantity. The real part tells us how the energy changes as a function of temperature. And the imaginary part is the scattering rate. It tells us, how often does it scatter into a different state due to phonons. Okay, now the question is, how do we combine these two kinds of interaction? So electron and hole and electron and phonons. So basically, how do we describe exciton-phonon coupling? There's been many attempts in the literature, sometimes completely neglecting electron-hole interactions, saying, okay, maybe if we're talking about hot electrons, maybe electron-hole doesn't matter. All right, but if we're really talking about bound excitons, we need that. Initially, people were using this approximation where they're saying, okay, well, we just compute the scattering rate for the electron, and the scattering rate for the hole left behind and add them up together and combine them with the exciton wave function that we can compute. But other people started using an approach based more on the Fermi's golden rule, and trying to compute this exciton-phonon coupling matrix element. And so the question is, how does this fit into a general theory of the exciton-phonon coupling? Right. So what we've done is basically work out the equation for propagating an exciton through the system. And so we're going to say, okay, so we're looking for some kind of self-energy, which again is a complex quantity, and the real part should tell us how the exciton energy change as a function of temperature, and the imaginary part should tell us how it scatters. And so we define this, so we have this fully interacting propagator, which is an electron and a hole that see each other and also see the phonons. But we define this intermediate quantity, which is an electron and a hole that don't see each other but do see the phonons. And so we give them fancy names so for each of them, and this is a graphical representation here. So this this line here, this L0 is just the bare electron and hole interacting through the system, forming an exciton, but not really interacting with the phonon or anything. If we turn on only the electron-phonon interaction, we get this smooth line here. But if we turn on the electron and hole interaction too, then we get this, well, at first, this really sharp spectral line that gets broadened a little bit by the interaction with electron and phonons. But what are these self-energy? Well, if we want to compute them, we need to work out these full quantum mechanical propagator equation. These C's are creation and annihilation operators. Right, so we make a few approximations. We say, okay, these excitons, we'll treat them as bosons, and assume that the band gap is much larger than the phonon frequencies. And basically, these are the diagrams we end up drawing. And so for each of these diagrams represent a matrix that we can compute. We can add them up, and okay, we've worked out each of the terms. And when we fully take into account electron hole and electron phonon interaction, we have these sort of diagrams where we can mix the interaction lines, and we work out the expression for computing them. This is what it looks like, the final expression, and it involves these exciton-phonon coupling matrix elements. Finally, we've applied this theory to a model system. So this is say a toy model that we can solve analytically for the electron and hole bands, but then we have to compute the exciton states and get the full excitonic spectrum. Then with some model interaction, we compute the exciton-phonon coupling matrix elements, and that gives us the temperature dependence of the energy states, and the broadening, which is the inverse scattering lifetime. And okay, basically we analyzed all of this and compared with the approximate expression that people were using in the literature, and showed that, well, unless you do the full theory, you're not even going to get the right order of magnitude for the scattering lifetime of the excitons. And finally, so very recently, some of my colleagues finally applied this theory to do the full ab initio calculation for the exciton lifetimes. And so in the end, they showed that they were able to reproduce the full, the experimentally observed exciton lifetimes or line width, so inverse lifetime. The only nuance here is that they had to compute the full self-energy matrix and diagonalize this matrix to obtain properly the exciton states coupled to the phonons. So that was I call this a success for this theory. All right. With this, I will just conclude and thank my students who are working on the first two projects mentioned on hydrogen absorption and MXC's materials. Thank you.
So we have time only for a couple of short questions. Well, I have one. Oh.
So, given my bias in statistical physics, how do you know if you use the wrong potential to sample, to generate configuration, even if you compute them after that with DFT, you're not sure to have sampled the right configurations?
Yeah, you're right.
So, I mean, how do you check that?
How do I check that? That's a good question. In principle, we should check that against fully ab initio molecular dynamics. We tried to do that, but it was very expensive, and we couldn't fully get all achieve a good sampling of all the states. We couldn't jump across barriers, so ultimately we have to rely on the mean error we see at each step, at each DFT step that we perform. One way to check that might be, so with this method, by sampling the configuration, we can also compute the phonon spectrum. So that's one thing that we can compare directly against experiment and against other perturbative methods. So that's as much as I can say. Michel?
Michel?
Can you tell us more about your machine learning potential? What does it involve, and is it accurate?
Yeah, so we're using so I'm not an expert in that. We're using the snap kind of potentials. There are other types of potential out there, but so far this is the one that's implemented. That's as much as I can tell you. Yeah.
Okay, maybe we should stop here and move to the next speaker.
Okay.